With this idea of exponential growth, right? We know roughly what it's talking about. Talking about things growing really quickly. And we have a graph that describes that, right? We know that the graph should look something like this. But we also have terminology to describe these things in exponential growth, right? For example, when I talk about dp dt, the first derivative, what's that phrase that I always talk about? That's what it describes. The rate of change. Okay, the rate of change. So dp dt is the rate of change. K is a part of this equation or this model. Okay, I also gave that another term. What did I call it? The growth rate. Okay, now this is where it gets a little bit confusing. In the syllabus, they actually refer to it as both. They call it the growth constant or the growth rate, which is slightly confusing because both of these have rate in it, right? But the key word here is growth. But the question is, when I was looking at this, I was thinking, hang on, what's constant about an exponential graph there? Because if you look at this graph, it doesn't seem like it's constant, right? Because it's growing really quickly. What's a graph that we usually call constant? Straight lines, right? We say that they're linear functions, right? Right? So it's yeah. So straight lines, we say that they're constant, don't we? Right? Because I guess when you look at the values, they're increasing by the same amount. Would you agree? Yes. Right? How is this constant? Well, if I give you an example, very simple exponential type of function, y equals to 2 to the x. Okay. Just have a think about these values here. When my x is changing, I want to see what's happening to my y. Okay. Just the first couple of values. We won't go too far. So for x equals to 1, what am I going to get my y to be? 2. That's just 2 to the 1, which is 2. What about when it's x is 2? Yeah, so 2 squared is 4. 2 cubed is 8. And 2 to the 4 is 16. What's constant here?
The rate of change.
Well, not the rate of yeah, so yes. Now this is where it gets confusing because I don't want you to confuse these terminologies here. What's actually constant here?
Times it by 2?
Yeah, is I want to say the rate of change. I want to say the growth rate, right? It's not constant. It has a constant ratio though, doesn't it? Right? So it has a constant.
Yeah, like T2 over T1.
It has a constant ratio. So I'm multiplying by 2 each time. I'm multiplying by 2 each time, aren't I? Right? Yeah. Does that make sense? So what's constant? Why do they call K a growth constant? Well, if you look at these ratios here, they're all the same. It's multiplying by 2 each time. Does that make sense?
Yeah.
That makes sense, right? Okay. But that's for y equals to 2 to the x. When I introduce a special type of function, a special type of exponential function, y equals to e to the x, I said that y equals to e to the x describes a special type of growth, right? It describes a special type of growth. Because when we, if I compare these two types of growth here, right? Compound interest and this exponential growth here with base e, they're very similar, but with a very subtle difference. If I have a spreadsheet here, when you look at this, we've got our compound interest formula and we've got our exponential model, right? So we know that P represents the principal, so what I start with, I've just made it simple. Let's say we start with like 1,000 people or something like that. And then I've got my rate and my K. When I talk about the growth constant, or the growth rate, remember, that's actually talking about the K value. Okay? That's talking about the K value. That's why I've written K is 4% and R is 4% there. Okay? We can think about them as very similar things. When I look at this, the compound interest formula and the exponential growth value, when I substitute these values in, what do you notice about these? They're pretty similar, right? If I start dragging this out, so I've just copied the formula multiple times over these terms. Just going to do it really quickly here.
Drag it down.
Okay. As these values are increasing, right? What do you?
Getting further apart.
Yeah. What do you know? So here there's a difference of just 0.8, but after the 11th term or the 11th year, what's the difference now? It's much more, isn't it? Yeah. Okay. Why is that happening? Well, if you think about the compound interest, think back to how, given the same time period, so given 1 year, how can I actually get more money out of that? Well, if I increase the number of terms that I have, do you guys remember that? So if it's compounded annually, I get a certain amount of money. But if it's compounded monthly, you get more. If it's and you say the more periods that you introduce to compound it, that will actually give you a higher final amount, right? But there was actually a limit to that. And the limit to that is really this model here. in this compound interest model, we're looking at discrete things. So even if I'm compounding every month or every day, those are whole number things, right? But the exponential model, that's talking about compounding things continuously. We use that word continuously. These whole number ones, we call them discrete things, right? As an example, why do we use this exponential model? Well, it's because when you think about things in nature or just things in the world around you, when you're growing, right, you don't say, well, like one day I'm this tall and then the next month I'm this tall. It actually happens over a period of time, doesn't it, right? It's saying every smallest unit you can think of, you're continuously growing. And that's how the exponential model works. And that's why the exponential model gives you a higher amount than the compound interest formula. Because the compound interest formula is doing discrete increases. Okay. Even though these values are still whole numbers, the exponential model is assuming that these increases that they're continuous. Okay. So that's the biggest difference. Does that make sense?
That one's like jumping like that.
Yeah.
Just like
Yeah, exactly right. So that's exactly right. That's why we have this gradual curve over here.